Hello everyone. Today is the 12th session of the exercise series of the electrical power transmission course. And today we will solve a question regarding the power system stability topic, which you have followed in the lecture sessions. So today we will have this question, which says, the synchronous generator is initially operating in the steady state condition when a temporary straight line to ground, so it's a symmetrical short circuit fault occurs on line L2 here at point F. The exact point is point F, and 5 cycles later, the circuit breakers B13 and B22 permanently open to clear the fault. If the infinite bus receives 1 per unit real power, so we have power here equal to 1 per unit, and also the power factor is equal to 0.95, and it's lagging. Calculate the maximum value of the power angle delta, and we have these parameters, h equal to 3, pm equal to 1, which will be constant during the 3 stages of the pre-fault, during the fault, and the post-fault. And also we would have the frequency equal to 50 Hertz. And the B section says that if breakers B13 and B22 open later than 5 cycles after the fault commences, determine the critical clearing time. So if in the first part, we know that when the circuit breakers open, so we know when we will have our post fault conditions. But in part 2, we want to find the critical clearing time which system remains stable, and so it's the most time frame that we have to clear the fault to prevent any instability in the system. So here we have the infinite bus or the Steve grid bus. It has a 1 per unit voltage in bus number 2, and other parameters that we have here, the active power and also the power factor. So as you may know from the lecture session, we need to form the power uh, equation for each stage. So for that, we need the internal voltage or the electromotive force of the generator. For that, we need a current in the network, and also we need the equivalent impedance to calculate the voltage drop in the route that we're going from generator to that point. So here, the parameters that we have is the active power here and also the power factor. So based on these values, we can easily calculate the current. So you may know that S is VI conjugate, right? So the magnitude of S would be equal to this. Then I would be uh, and you may know that S is equal to P with the power factor, right? So then we would have PV in power factor. And also I is equal to magnitude of the I with, because it's a lagging, minus cos inverse of the power factor, right? So we have this formula, so we calculate the magnitude of the current here, we then put here, and then we calculate the angle of the arguments of the current as well using this formula. So, and also we need to calculate the equivalent impedance between the generator and also the infinite bus. So we have these impedances, which these are in series, so they should be summation, and these are in parallel, and also this summation here. So we calculate the equivalent impedance between generator and bus number 2, which would be equal to J 0.52 per units. Then using this formula, we calculate the current, which we have this value for it, 1.052 with argument of minus 18.19 per unit. So so we calculated the equivalent impedance and also the current going into bus number 2. Then by having it, then E would be equal to V2 plus X in I, right? This is our voltage drop between the generator and bus number 2. So yes, sorry, this should be xi, or maybe we can see it like x itself contains the j, but here we have seen like this. So therefore we have j here. And then we would have 1 plus j 0.52 multiplied by the current, which is this current. And at the end, we will have the electromotive force of the generator equal to this number in per units. So in the pre-fault condition, right? So we calculated the impedance in pre-fault condition. Remember, we still have this circuit breakers closed, so we have this line connected. Based on that, in steady state conditions, we have PE equal to PM, right? So based on that, we calculate the electric power, and it can be calculated using this formula. Then we have PE equal to 2.4638 in sin of delta. So as I mentioned, PM is equal to PE, and it's equal to 1 because it's constant during all of the solution, all of the stages of the fault occurrence and fault clearing processes. So, and also we have delta 0, which is the steady state angle of the voltage just before the fault occurrence, which is a constant value. So here then delta 0 can be easily calculated, and it would be delta 0 equal to 0.41 radian. So we calculated delta 0, which is the delta we have in the pre-fault condition. Now we want to study in the time that the fault is the fault exists in the system. So in these conditions, we don't deal with steady state calculations. Instead, we use swing equation. You know from the lecture, which can be written like this: Pm minus Pe regarding the delta we have at each time, then h divided by pi in frequency and multiplied by the second derivative of delta in respect to the time or t. So we know that we had 5 cycles to open the circuit breakers to clear the fault, right? So t is 5 cycles. Then we have the frequency which uh, can be used to calculate the total duration with 5 cycles. So it should be 0.1 seconds. So in 0.1 seconds, we open the circuit breakers. And in this condition, we use the swing equation to find the equation for electric power of the generator. So this equation easily can be converted to this one. And during the fault, we consider that the delta uh, is the delta zero is still equal to the delta that we had. And because we had the steady state condition, then the variations of delta at moment zero or t equal to zero, which is the moment that we see the fault, the variation of delta is still zero related to the steady state that we had in the pre-fault conditions. And using these conditions, we solve this differential equation, which yields this, the delta at each t would be equal to this. All right, we have a delta zero, we have Pm, and we have other parameters like omega and h. And also one thing should be taken into account that because we have the fault near to the generator, the Pe is relatively equal to zero. So we consider it equal to zero, and we put this parameter equal to zero. All right. So by this consideration, we can reach this solution for the delta equation. So then our delta 1, which is the fault uh, clearance, would be 0.1, which is 5 cycles. We calculated the time duration. And by putting t equal to 0.1 in this equation, we can calculate the delta 1 equal to 0.6797 radiant. Represent the time or the moment that we clear the fault and its related delta. So delta 1 is the delta that we have during the moment that we clear the fault. Okay, so we calculated delta 0 for the pre-fault condition. we calculated the delta 1, which is the delta related to fault clearance moment. And then we want to study the system after the fault clearance. So you know that we open two circuit breakers, which are here B13 and B22. So we only would have this reactance, this line reactance. So we need to recalculate the equivalent impedance between the impedance or reactance between the generator and the infinite bus. So we now have the summation of those three, the generator, the transformer, and the line. Then our equivalent Thevenin reactance would be J 0.60 per unit. So by having the new J, we again, new X, we again form the electric power equation because after the fault clearance, we again have steady state condition, right? So by this, we have 2.1353 seen of delta. All right. So uh, this is our post-fault equation. So now we want to form the accelerating and decelerating uh, uh, regions, which A2 should be equal to A1, right? To maintain the stability of the system. So for that, we have this area A1 and this area. So A1 is the value under PM from delta 0 to delta 1. So this is the area we got, right? And the delta 2, sorry, the A2 is the region between this figure here and this one. So it should be PE2. This figure is for the post-fault condition, right? So you know this from this this section. Okay, so if we put A1 equal to A2, we can easily calculate the desired value for delta 2, how much our delta will be increased uh, until we can reach the stability in the system. So by putting these regions equal to each other, we would have delta 1 minus delta 0 equal to 0.2618. And, uh, and also we would have these equations, right? This equation. So we calculate delta 2 from this, and then calculate delta 1 from this, or this. So then we have this, A1 equal to this, and we calculate A1, which is equal to 0.2618. And as I mentioned, A2 should be equal to this one. So we have the formulation for A2, and then we make it equal to this. So by solving this, we can have delta 2 equal to 1.2108 rod. Okay. So we calculated the maximum delta for this uh, condition when we clear the fault after 5 cycles. And the part B asked us to find the critical fault clearance time when the circuit break activation time is beyond 5 cycles. Okay, for that we uh, we need to consider uh, the post-fault condition of the network, which you can see here, right? We need delta max, which is the maximum delta we witness when we clear the fault in critical time, maximum critical time. And after this delta, the system will face the instability in its behavior. So for that, after the fault clearance, we would have the steady state condition, and we would have this network, and then we have calculated before that uh, our PE2 would be like this, right? So it's the same for us here. The only thing that in a steady state PE2 is equal to 1 per unit, then we can calculate the delta 02 uh, easily using this formula. And then it would be equal to 0.4874 radian. And then delta max can be equal to this pi minus delta 02. You know that sin of delta is equal to, right? So using this, we calculate delta max, in which we face the instability in the system. So here again, we form the integrals of the regions to find the critical uh, the critical angle that the fault needs to be cleared before any instability occurs in the system. So, so we would have from first equation delta critical minus 0.4179 would be equal to A1, and A2 would be equal to this, and by having this A1 equal to delta critical minus 0.4179 and A2 equal to this, we can easily calculate delta critical, which here is equal to 1.4063 radian, which is equal to 80.58 degrees. And at the end, we use the swing equation to find uh, the time which we have the critical angle that we calculated. So for that, we put the data, the angle value there, and based on that, we calculate the time. So using this, we would have 9.7 cycles or 0.1943 seconds. So we have this window for fault clearance, which is a fairly short time, which requires accurate uh, and advanced protection and also circuit breakers to be activated by occurrence of this fault. Okay, thank you very much. This was the question we considered for the power system stability part. Please feel free to ask me and send me email if you have any question about these sections. Thank you and have a nice day. Bye bye.